Now that the X-rays have been produced, let's discuss their interaction with matter. There are two interactions which will affect the final intensity of radiation at the detector. These are the absorption of X-rays and the scattering of X-rays. We will introduce two measures to quantify the effect of these interactions. These are the cross-section of interaction and the mass attenuation coefficient. Let's firstly discuss the cross-section of interaction. When photons pass through a material, some will interact with the matter present and some will not. The cross-section is defined as the probability of one photon interacting divided by the number of them passing a material per unit area. It is measured in meters squared, or more commonly barns, which is 10 to the minus 28 meters squared. Let's now discuss the second measure, which is mass attenuation coefficient. Consider a flux of photons, phi, entering a thin layer of material of thickness dz. The flux exiting the material will be reduced by some amount d phi due to the interactions occurring within the material. We can write an equation for the change in flux per unit length, where it is proportional to the number of interaction centres per unit volume, the cross-section of interaction, and the flux present at that point. The minus sign in this equation indicates a decrease in flux as the photons travel through the material. The differential equation is separable and can be integrated to give the following equation for flux as a function of z, where phi naught is the initial flux. This equation shows that there is an exponential removal of photons in a material. The product n sigma, which you've seen in these equations, is the linear attenuation coefficient. It is denoted mu and has dimensions of inverse length. It is a measure of how many photons are absorbed per unit thickness of the material. It's a useful quantity, however, it is density dependent. Consider compressing a slab to half its thickness. As n doubles, mu will also double. A more general measure of absorption is given by the mass attenuation coefficient. This is mu divided by the density, and is independent of the density of a material. This again defines how quickly the flux of a photon beam decays. Let's now discuss the source of these interactions in more detail. The first interaction I'd like to mention is the absorption of X-rays. 90% of the photons which are sent into a patient are absorbed, and this is caused primarily by the photoelectric interaction. An X-ray photon is absorbed by a bound orbital electron. The binding energy of tissues is often smaller compared to the energy of the photon, so the atom in the tissue is usually ionized and a photoelectron emitted. The energy of this photoelectron, E subscript Pe, can be calculated by subtracting the binding energy of the material away from the initial energy of the photon. This is of course given by its frequency nu times the Planck constant h. The mass attenuation coefficient for photons involved in the photoelectric interaction varies. This is dependent on two main factors. Firstly, the atomic number of the atom at an interaction site, and secondly, the energy of the photons involved. The mass attenuation coefficient is approximately proportional to the atomic number to the fourth power, and inversely proportional to the energy of the photons to the third power. The attenuation's dependence on atomic number allows a strong contrast between bone and soft tissue on a detector. For example, bone has an average atomic number of 13, while tissue has one of around 5. Let's now discuss the attenuation's dependence on energy. As the energy of the photons increases, the attenuation decreases with approximately 1 on E cubed. Notice that I've drawn a log-log plot here. There are certain discontinuities in this plot, however, which demonstrate an increase in the attenuation at specific energies. These are known as absorption edges. These peaks occur due to the energy of the incident photon being extremely close to the binding energy of a specific electron. This massively increases the probability of interaction. The edges are labelled in correspondence to the electron's principal quantum number n. For example, k edges correspond to n equals 1, L to n equals 2, and m to n equals 3. You will notice that some absorption edges are staggered at the top of their discontinuity. This staggering is due to electron orbitals of the same principal quantum number having very slightly different energies. These differences are due to electrons having different angular momentum quantum numbers and spin values. The next interaction that we'll discuss is Compton scattering. This describes the interaction between a photon and a free electron. An incoming photon of energy hν, where nu is the frequency, collides with a stationary electron. The electron recoils at some angle phi, while the photon decreases in energy and therefore frequency, and is scattered at some angle θ. The resulting photon has energy hν', where nu' is the new frequency. It should be noted that no electron is in reality free, although we can approximate it to be if the binding energy is considerably less than the energy of the incident photon. This is often the case if X-rays are incident onto tissue. X-rays can have energies up to 150 keV, while the binding energy of tissues is just a few keV. Let's now quantify the energetics of the Compton interaction using the following formula. This relates the final energy of the photon to its initial energy, as well as its scattering angle θ. m0 is the rest mass of the electron in the interaction, and c is the speed of light. The scattered photons which are produced travel in all directions and strike the detector. They therefore degrade the quality of the image by reducing contrast. The probability of Compton scattering is independent of both the atomic number of a material and the energy of the incident photons. This is in contrast to the photoelectric effect. Compton scattering therefore has a pretty constant contribution to the overall mass attenuation coefficient. The contribution is independent of both energy and atomic number. We can consider the overall mass attenuation coefficient as a sum of contributions from both the photoelectric effect and Compton scattering effect. Consider the contribution of each as a percentage of the total as the energy of the X-rays increases. As discussed, the photoelectric effect decreases in significance at higher energies, and the constant contribution from the Compton effect therefore becomes more significant. Thank you for watching. I hope you learned something about how X-rays interact with matter and how we quantify these effects. Join me in the next video where we'll be discussing how X-rays are detected and a final image is produced.